Okay, welcome back to part two, perhaps part three, depending on how I have to break this up. And this is still chapter 14. This next few slides are about the various types of weathering. Weathering is just a term that refers to the breaking down of rock that's at the surface, and then also it occurs some depth below the surface. Rock gets disintegrated down into smaller particles, into gravel, then to pebbles, to sand, and as you're going to see, then silt and clay. There are two types of weathering process. Some is physical, and that's sort of mechanical weathering, and the other kind is chemical, which is something that happens to rock in the presence of water. There's a chemical reaction and water causes things to change, and we'll explore these slightly more in the next few slides here. So let's start back up a bit and take a look at this image here that shows sort of a cross-section of what the earth would look like, and you can see these sorts of things on road cuts on the highway. At the bottom, we have closer to the center of the earth, of course, is bedrock. And when bedrock is broken into bits and pieces, it becomes, crumbly, then that's called regolith. Regolith helps form, is the parent material for soil. Soil is developed along with things that come from above, like dead leaves and dead grass and that kind of stuff. In those places where you can see the regolith or even the bedrock, is called an outcrop, where it's bare rock is exposed to your vision. It's not covered by soil. Just this vocabulary term, parent material, is either consolidated or unconsolidated. The consolidated is bedrock, or unconsolidated is the regolith. That's the material from which soils develop. Here's just an image of here's the rock and the regolith, and it has been eroded and transported out here where it's become the dirt. So this is the parent and this is the child, so to speak. And here is an image of the same thing in Mars, or on Mars. We have geographers and geologists, some actually from CSUN Geography Department, that have worked with NASA and JPL over in Pasadena to examine these photos taken on the surface of Mars and sent back, and to analyze them, because you can understand a lot of the Martian processes if you understand the Earth processes. To me, it's clear that Mars once had lots of water. Otherwise, you wouldn't see the erosional features on so many of the rocks that are laying there. So what are the factors that influence weathering processes? One is you start with the parent material. What kind of rock is available for weathering? And one of the most important things is what kind of joints, how is the rock being kept together? The second thing is, what's the climate like? Hot and rainy breaks down rocks much faster than cold and dry. How much water is either at the surface or underneath the surface? Where is the rock? Is it on a hillside or is it on a flat plain? What kind of vegetation is around? Because vegetation helps break down rock into soil as well. Joints are fractures or some kind of separation in rocks that occur without displacement of the sides, meaning they're just cracks in the rock. Eventually, there will be displacement, well, not always, but frequently along the joints. Some types of rock have lots of joints, predictable joints, easy to break apart joints, and others don't. Those rocks that do have lots of joints are susceptible to a lot more physical and chemical weathering. Why? Because there's more rock exposed to the processes. So rain, temperature, and how much freeze-thaw action you get have a lot to do with the speed at which rock is broken down from bedrock and regolith to dirt, essentially. Physical weathering dominates in drier and cooler climates because there are less chemical processes going on, and then chemical weathering dominates in wetter and warmer climates. Not 100% true, but those trends are general. So let's talk about hillsides, because that's a weathering process. If rock on a hillside is exposed to the sun or wind or a lot more rain, then you will get more erosion. Slopes that face away from the sun, so they are northern facing slopes here in California or in much of the United States, they tend to be cooler, moister. They may have more vegetation on them, which might expose them to some additional erosion or chemical and physical weathering. Take a look at this photo I took a number of years ago, and this is a slope that faces away from the sun, and this is a slope that gets full sun. So the sun is always beating down this way. This slope is in the shade a lot, and this is in the sun. Because it's in the sun, it is drier, and because it's drier, it has less vegetation than this side, which when it gets rain or fog drip or something like that, it manages to hold on to that moisture more, which then prompts vegetation to grow, and that sort of has a mutually reinforcing feedback loop. And so this side is vegetated and this side is not, and that has implications for which of these slopes is going to erode most quickly. Sometimes vegetative cover protects rock by shielding it from the raindrops, which the world's most erosive or corrosive element is water. Roots can stabilize soil, and that's why you like to see plants regrow on a hillside quickly after a wildfire, because that helps the soil from coming down the hill. But roots can also produce organic acids and enhance chemical weathering, which is important on certain types of soil, as we're going to see. Plant roots can also break up a rock, and if you've ever driven on some of the twisty, windy highways up into the hillsides, you'll see pine trees growing right out of the side of rock. And those pine trees are amazing that they can do that, but they will eventually wedge open rock. I had this viney stuff in my backyard called creeping fig growing on the walls, and it was breaking up the concrete blocks that make up the walls. That's how strong plant roots can be. Physical weathering processes include frost action, sometimes known as frost wedging, which will break apart rock, and then salt crystal growth, which salt crystals will break apart rock. And do we have, oh, no. The pressure release jointing. So basically what happens is that ice will wedge open a crack in the rock and then thaw over and over again. And it's like driving a hammer into rock. Salt crystal can grow as well. This will happen where it's cold enough to get lots of freezes. This happens where you have water running through the cracks in the rock, the joints in the rock, and in a dry climate. So when the water runs through the cracks and then becomes exposed to the dry, hot climate, the water evaporates, but the salts that were in the water remain behind, and those salts grow in a crystalline fashion and will wedge open rock again like a hammer. So what kind of weathering do you see here? Well, you see that there is a lot of two things going on. There's chemical weathering, and we're going to see oxidation. You can see the rustiness, but you see that there was a break in the rock here, and a big chunk came off, and that because it's, I think you can see it's a deserty landscape, that could have been salt crystal action. You can see the salty deposits here going down the side of this hillside, this rock. But it was also sort of out in the Mojave where it does get cold enough to have some frost action, so it could have happened during a freeze event as well. So here's this frost wedging, and you can see that rock breaking apart. Water expands by about 9% when it freezes, and it's extremely powerful. It's enough to explode a can of soda in the back seat of your car if you leave one in there during a cold night and in a northern climate. And then here's that salt crystal growth as well. The last type of mechanical weathering we're going to see is called this pressure release jointing. And basically, as layers of rock peel off, they release pressure on the inner parts of the rock, and what you get is something called exfoliation, which is just like your skin peeling off. If we were to pile tons of rock back onto these layers here, they would be smashed down and could not exfoliate. But as things get chipped off, as layers get chipped off, the pressure from within helps the rock break apart. Here's a big exfoliation, the most famous version of it in the world, probably here in Half Dome in Yosemite. If you've never been there, definitely get up to see here. This is Half Dome. The other half broke off, and you wouldn't have wanted to be below that. Here's some exfoliating in a sheet style fashion in Scandinavia, and though you can see, you know, the bits and pieces that have broken off laying there below it. I've even found it in the local hills here. You can see the exfoliating on a hike up to Calabasas Peak as the upper layers chip and peel off. The layers below are exfoliate like layers of skin, and they chip away and weather. There's some chemical weathering processes too worth talking about. Spheroidal weathering, and you can see this on Calabasas Peak if you hike up there too, but for some reason I can't find the pictures. And what you get with this spheroidal weathering are rounded rocks. Chemical weathering generally occurs in the joints and the fractures as well. Here's some of these roundy looking rocks here. You can find these in local hikes as well. And there's chemical weathering here going on in the joints that dissolve weak minerals. This is the Alabama Hills, which are not far from here as well. You can go and witness this yourself. All right, and we're going to pause here before we move on to a special kind of weathering, and chemical weathering called Karst Topography.